Welcome back. Problem 6-191. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Materials by R.C. Hibbeler. Statement is determine the shear and movement in the beam as a function of x, where x is greater than 0 and less than 6 feet. Draw the shear and movement diagram for the beam. So you can see this is the cantilever beam, clear, where there is a point load at this end, which is 8 kips. At a length of 4 feet, we have clockwise movement of 50 kips into feet, and there is a distributed load from fixed end till the length of 6 feet, and the magnitude is 2 kips per feet. So we have to determine the shear and movement equation in terms of x for the region x is greater than 0 and less than 6 feet, and then we will draw the shear force and bending moment diagram. So let's start with the solution. If we remove this fixed support at this end, so we will be having a reaction force. Let this is your point number 1. So there will be reaction force, which is R1, and there will be a moment as well. Clear? So this we will find this R1 and M1 by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point 1 is equal to 0, and taking the counterclockwise moment as positive. So about this point 1, one moment will be due to this 8 kips load, and the perpendicular distance is this 10 feet. And this is producing clockwise moment, so it will be negative. So I will write minus 8 into 10. The second moment is this one, which is 50 kips per feet into feet, and this is again clockwise, so it will be also negative. So minus 50. Now you can see you have a distributed load, so we will convert this distributed load into a point load. So for that, we will multiply this 2 kips per feet with the length over which it acts. So 2 into 6, which is 12, and this load is acting downward, and that will be acting at a half of the total length. The total length is 6 feet over which this distribution load acts, and the half will be 3 feet. Okay, so the third moment will be due to this 12 kips load, and perpendicular distance is 3, and this is also producing clockwise movement, so it will be negative. So I will write minus 12 into 3. And the last moment is this reaction moment, which is counterclockwise M1, and that will be positive. But the sum of all moment about point 1 must be equal to 0. So from here we will get M1 minus 80 minus 50 minus 36 is equal to 0, and we will get this M1 will be equal to 166 kips into feet. So this is the reaction moment when you remove this fixed support. Now we'll find this R1 by using equation of equilibrium, that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So R1 is upward, 12 is downward, that will be minus, and minus 8 will be, their sum must be equal to 0. So R1 minus 12 minus 8 is equal to 0. So it means that R1 is equal to 20 kips. Now you have R1 and moment M1. So what we will do is that we will section this beam in the range of x is greater than or equal to 0 and less than 6 feet, and draw the free body diagram. So if I draw it over here, let this is the beam. This is point 1, where we have a reaction force R1. R1 is 20 kips, and the moment was, we calculated, is 166 kips into feet, that is counterclockwise. And this length which we have cut the beam is x, and there is a distributed load over a length of x, and this distributed load is downward. So when you convert this distributed load into point load, so it will be acting at the mid, clear, and the magnitude of this distributed load is 2 kips per feet. So this point load will be equal to 2 into x, and that will act at a half of the x. So this will be equal to x by 2, and the remaining will be also x by 2. And when you cut the beam, you will be having a shear force that will be, we will take it downward, V, and you will be having a reaction moment M. So we'll find this V and M in terms of x. How we'll find this? So by using equation of, let this is point O. So we'll find this M and V by using equation of equilibrium. This equation of equilibrium is that sum of all forces along y direction must be equal to 0, and upward force is taken as positive. So 20 is upward, minus 2x is downward, and minus V, their sum must be equal to 0. So 20 minus 2x minus V is equal to 0. So from here we will get V is equal to 20 minus 2x, and the unit will be in kips. This is your shear force. Let this is equation number 1, which is the equation of shear in terms of x, and this is for region x is greater than or equal to 0 and less than 6 feet, where we have cut the beam. Now we will find this moment by using equation of equilibrium, that sum of all moment about point O is equal to 0, and taking the counterclockwise movement as positive. So about this point O, the first movement will be due to this 2x and perpendicular distance is x by 2, and this is producing clockwise movement, so it will be positive. So I will write 2x into perpendicular distance is x by 2. The second moment will be due to this 20 kips load and perpendicular distance is x, and this is producing clockwise, so it will be negative. So I will write minus 20 into x. The third moment is this 166, that is counterclockwise movement, so it will be plus. So I will write plus 166, and the last moment is external moment, which is considered as counterclockwise, so it will be also positive, and their sum must be equal to 0. So from here you will get m plus x square, because 2x into x by 2 will be x square, minus 20x plus 166 is equal to 0. So this moment equation will be equal to minus x square plus 20x and minus 116, and the unit will be kips into feet, and this is equation number 2. So equation number 1 and 2 are shear force and bending moment equations in term of x, and here you will use x is greater than 0 and less than 6 feet. Clear? So this is the answer of our first part. Now we'll move toward drawing the shear force and bending moment diagram. So for what we will do is that we will take the vertical line from the end of this beam, and first we will draw the shear force. So for shear force I will take a horizontal line to show length x in feet, and on y-axis we have shear force and unit will be kip. Clear? So let one division is equal to 5, so 5 plus 10 plus 15 and plus 20, and similarly downward that is minus. Okay, so for region of, if I draw a table, clear, and the table will be like that, x value shear force in kips and moment will be kip into feet. So for x is equal to 0, you can put it in this equation number 1. So when you put x is equal to 0, this v will be equal to 20. So I will write v will be equal to 20 kips. And for x is equal to 0, so this will be 0, this will be 0, and moment will be minus 166. So I will write minus 166. Similarly, for region of x is 6 feet. So if you put x is equal to 6 feet, so it will be minus 12. So 20 minus 12 will be equal to 8 plus 8. So v will be plus 8. Similarly, you put x is equal to 6 feet in this equation, and you will get moment will be equal to minus 82. Okay. So for x is equal to 0, we have v is equal to 20. So what we will do is that for x is equal to 0, our first point is this one. Clear? And for x is equal to 6 feet, so this is 6 feet length. We have shear force is 8 plus 8. So we will locate plus 8. So plus 8 will be somewhere here. Let me choose the point. This will be plus 8. Now you can see that shear this loading is a uniformly distributed load, or load with a horizontal line and of 0 degree. So shear force will be 1 degree higher as the load is downward. So it will be a linear, the shear force will be a linear line and slope will be decreasing. So we will join these 2 points using straight line. So this will be the loading. Now in moving from this point till this point, we do not have any other force, so shear force will remain horizontal. So it will be remain horizontal till the end, and at the end you can see you have minus 8 downwards, so that will cause it toward downward 0. Clear? So this will be your shear force diagram. Now we'll draw the bending moment diagram. So for bending moment diagram, I take the horizontal line to show the length x in feet, and on y-axis we will having moment that will be unit kips into feet. Let one division is of 100, so minus 100, minus 150, and minus 200. So for x is equal to 0, we have moment is equal to minus 166. So minus 166, let minus 166 is this point. This is minus 166. And for x is equal to 6, we have moment is minus 82. So let minus 82 is this point. Minus 82 is this point. Minus 82 kips into feet. Now you can see that shear force is a linear line with slope decreasing. So bending moment will be second degree curve, and it will be in clockwise. Rotation will be in clockwise direction. So we'll join these 2 points by using a curve. Okay. At this point, you can see you have external movement of 50 kips into feet, that is clockwise. So while drawing in bending moment diagram, it will cause the bending moment to go upward. This is convention given in the book. So minus 82 plus 50 will be equal to minus 32. So bending moment will change to minus 32. So let this point is minus 32. So your bending moment will change toward this. Okay, and the last one is this area under the shear force diagram, and you can see this area is, this height is 8 multiplied by length is 4. So 8 fours are 32. So minus 32 plus 32 will be equal to 0 at this point. So you will get the shear bending moment 0 at this point, and we will join these 2 points using a straight line clear, and that will be your bending moment diagram, and which is the answer of our second part. So that was all about problem 6-191, in which first we solved the shear force and bending moment equation in term of x, and then we draw the shear force diagram and bending moment diagram. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 6-88. This problem is taken from chapter number 6, that is bending, and book name is Mechanics of Material by R.C. Hibbeler. So statement is, if the beam has a square cross section of 9 inch on each side, determine the absolute maximum bending stress in the beam. So you can see this is a cantilever beam, that is, and A is fixed, and from A till a length of 8 feet we have uniformly distributed load, and at point B we have a point or concentrated load of 1200 pounds, and the cross section is that this is a square cross section 9 inch by 9 inch. So you have to determine the absolute maximum bending stress in the beam. So let's start with the solution. So first step is that if you remove this fixed support at point A, so you will be having a reaction force which is represented RA, and you will be having a moment which will be MA. So we will find this RA and MA by using equation of equilibrium. So first equation of equilibrium is that sum of all moment about point A is equal to 0, and taking the counterclockwise moment as positive. So you can see this is counterclockwise movement, so it will be positive. So I will write MA. The second movement will be due to this load, which is 1200, and now perpendicular distance is 16 feet clear, and this is producing clockwise, so it will be negative. So I will write minus 1200 into 16. The third load is due to this uniformly distributed load, so we will convert this uniformly distributed load into a point load, and that will act at the middle of this 8 feet. So this distance will be 4 feet, and this remaining will be also 4 feet. Now this distributed load when converted into point load, so it will be equal to 800 over the length, entire length over which it acts. So this will be equal to 6400 pounds. Now due to this load about point A, the perpendicular distance is 4 feet, and it is also producing clockwise, so it will be negative. So I will write minus 6400 multiplied by 4 is equal to 0. So from here you will get MA will be equal to this 1200 into 16 will give you 19,200, plus this 6400 into 4 will give you 25,600. So when you add them, you will get moment about A comes out to be 44800 pounds into feet. So this will be the moment. Clear? Now we will find this RA by using equation of equilibrium. The second one, which is sum of all forces along y direction, must be equal to 0, and upward force is taken as positive. So you can see RA is upward, minus this 6400 is downward, minus 1200 is downward, and their sum must be equal to 0. So I will write RA minus 6400 minus 1200 is equal to 0. So from here you will get this RA will be equal to 7,600 pounds. Now you have RA and RMA. So what we are going to do is that we will draw the shear force and bending moment diagram, and from there we will take the maximum bending moment. So what we will do is that we will take vertical line from the end of this beam, and similarly a vertical line from the other end of the beam, and then there is a horizontal line to show the length in feet. So X will be in feet. On y-axis you will take the shear force, that will be in pounds. Okay, let one division is 2000. So 2000, this is 4000, this is 6000, this will be 8000. Okay, now at point A we have RA, which is equal to 7600. So what we will do is that we will plot 7600. Let 7600 is this point. Okay, now if you take a vertical line from this, so this length will be 8 feet and this distance will be, the other one will be also 8 feet. Clear? Okay, now we want to find the shear force at this point. So you can see the shear, this is the load which is 800 over the length which it act is 8, so it is 6400. So what we will do is that this is downward force, so this force will be minus 6400. So 7600 is there, minus 6400 will cause it to 1200, plus 1200. So over here we will have plus 1200. So let plus 1200 is this point. This is 1200. Now you can see that this load is straight line, clear, is of 0 degree, so shear force will be 1 degree higher and it will be a straight linear line and slope will be decreasing because this load is downward. Now moving from this point till end, there is no other shear force, so it will remain horizontal till end, and at the end you can see you have minus 1200. So plus 1200 minus 1200 will bring it to 0, so it will come down. So this is your shear force diagram. Now we'll draw the bending moment diagram. So for bending moment diagram, I will take a horizontal line to show x in feet, and on y-axis we have moment having unit pounds into feet. Okay, let one division, you can see the moment is in 10,000, so we will take one division is 10,000. So downward is minus 10,000, minus 20,000, minus 30,000. Similarly, this will be minus 50,000. Now at point A, you can see you have a moment of MA, which is 44,800 pound into feet. So this is counterclockwise. While drawing it on bending moment diagram, this counterclockwise movement will cause it to toward downward. So we will locate it as minus 44,800. So let this point is minus 44,800 pounds into feet. Now area under the shear force diagram will give you the bending moment. So this area, you can see this is trapezoid. This length is 7,600 and this height is 1200. So how we'll find this area? Let this area is A1. So A1 will be equal to this height, which is 7,600 plus this height. So I will write it 7,600 plus 1200 divide by 2 into this breadth, which is equal to this breadth, which is equal to 8 feet. This is how we find the area of trapezoid. Okay, so when you solve this, this area will be equal to 35,200. Now here the moment is minus 4,480 minus 4,480 plus this 3,5,200 will cause it to change it to minus 9,600. So at this length we will have minus 9,600. So let this point is minus 9,600 pounds into feet. Now you can see that this shear force is a 1 degree line and slope is decreasing. So bending moment will be the second degree curve and it will be in clockwise direction. So I will join these 2 points by using this curve. Clear? Now the second area under the shear force diagram is this area. Let this area is A2. So you can see A2 is equal to this height. This is rectangle. So this height multiplied by this width. So 1200 multiplied by 8. So 1200 multiplied by 8 will be equal to 9,600. So minus 9,600 plus 9,600 will be equal to 0. So bending moment will be 0 at this point. So our new point will be this one. Clear? Now you can see that shear force is a horizontal line with 0 degree and this is positive area. So bending moment will be 1 degree higher. It will be a linear line and slope will be increasing. So we will join these 2 points using straight line. So this is your bending moment diagram for this beam. Now from BMD, bending moment diagram, we can see that maximum absolute value of bending moment is equal to, you can see one is this one, the other one is this one, and third one is 0. So this is the maximum value. So minus 44800 and unit will be pounds into feet. So this maximum bending moment absolute value will be equal to 44800 pounds into feet. Now if you want to convert it into kips, so 44.8, it will be kilopounds, which is equal to kips into feet. Okay. Now if you want to convert this feet into inch, so what we will do is that 44.8 multiplied by 12 and the unit will be equal to kips into inch, because 1 inch is equal to 1 feet is equal to 12 inch. So this is the maximum bending moment, and we know that maximum bending absolute value of bending stress is equal to maximum bending moment into C divided by I. Since we have been given a square cross section of 9 by 9, this is 9 inch and this height is also 9 inch. So we will find the moment of inertia for this beam, and if we take the half of this will be its neutral axis NA, and for this I is equal to, I for rectangular or square is 1 over 12 BH cube. So here B is 9 and H is also 9, so 9 power 3, that will give you I. And when you calculate this I will be equal to 546.75 inch power 4. What about C? So C is distant from neutral axis till top or bottom, so this are C, which is equal to 9 divided by 2. So C is equal to 9 divided by 2, which is equal to 4.5 inch. Clear? Now you have all the values. You can just put it in this formula. Maximum absolute value of bending stress is equal to moment, which is equal to 44.8 multiplied by 12. Unit is kips into inch, divide by I, which is having 546.75 inch power 4, and C is 4.5 inch. So we will left with we will get 4.42 kips, which is kilo pound, clear, divided by inch square, and that is maximum absolute value of bending stress. And when you calculate it, this is maximum absolute value of bending stress is 4.42, and kips per square inch will be equal to KSI, which is kilo pound per square inch. And that is the answer of our this question, in which we have calculated the maximum absolute bending stress for the beam and loading shown. I hope you have enjoyed this video. If you are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.